So, let's actually dive into some real stuff, though, right? I think it's about time, anyways. Last time, some of the stuff that we've been talking about, we talked about kinetic energy, we talked about work. Today, we're going to expand upon those details a little bit, but you might remember some of these slides right here. Relaxation doesn't exist within the College of Engineering, neither does it exist in the College of Science. Arts and Science, I guess. But anyways, brief recap on some of these details. We had two big equations for work. We said there was one of these that was very general that we could use for just about everything, right? It looked like this. It was a nasty integral. We said, yikes, that's terrible. But we don't need to worry about it if we have a constant force over the duration of our displacement, right? If we have a constant force, then it turns into this very nice thing. And the reason that we have to specify that these are both vectors is because, remember, this is a dot product, not just multiplying. We're not just taking magnitudes, we're taking a dot product between those two vectors, and that is a very specific type of vector multiplication. So, the general gist of it, though, is that if I exert a force on an object over some distance, I am putting some energy into that object. And how does that energy manifest? Well, it typically manifests as kinetic energy. The kinetic energy of any object is 1/2 mv squared, which any type of energy is always just some sort of quantity. It is not a vector. I don't have an energy going upwards. I have a velocity going upwards and an energy associated with that velocity, but the energy itself does not go upwards. So those are two big things that we had from last time, right? And then there was this fancy little theorem here. The work kinetic energy theorem is the idea that exactly what I said. Right? Anytime I put work into an object, then the change of kinetic energy is equal to the work done on the object. That is to say, if something is already moving, it already has some kinetic energy. If I start to push on it while it's moving, then it'll change the kinetic energy. It doesn't just automatically equal the kinetic energy, it is equal to the change of kinetic energy. Right? I can do negative work. I can stop an object from moving, or I can make it start moving, or I can make it move faster. Any of those details will work. All of that gets included in this nice pretty equation right here. So, the power of science. Let me go into the animations on this one because this is a little bit intense. So, let's consider this problem. I have a block, right, as I often do, at some place with some initial velocity, going some distance d, and there's no friction on that surface, right? It makes it nice and easy. Let's assume that I know how far it travels, and I know that there's a force acting on it. How might I find the final velocity of this object? Well, with our brand new work kinetic energy theorem, this is actually not so bad for us. See, what we can do here is we can say, all right, well, dynamics would tell me that the acceleration is equal to the force divided by the mass. Kinematics could take that acceleration and find that final velocity right from that thing. Right? Fantastic. We have seen this stuff before. We've been working with this for a little while now. That's one way to do this, right? And that does technically work. There's a nasty radical there, but, V naught squared and everything else. We know these tools. We're familiar with them. Even if they are a little bit clunky sometimes, we're familiar with these tools. The other way I could do this is I could use work and energy instead. And in the exact same way, I could say, well, I started with some kinetic energy. I ended with some brand new kinetic energy. The difference between those two must be equal to the work done. Now, I'm going to pause right here. There might be some critical detail I am missing. And what might that critical detail be? What could happen to these velocities that would completely invalidate what I'm trying to do right here? It's not that they could be equal. That's close, though. That's on the right track. If they're equal, then I would know my net work would be 0 unless... what? What are we thinking here? What's the scenario that kind of messes all of this stuff up? It's not even that we're not moving necessarily. That's all fine. That's actually easy to deal with. That's the easiest case to deal with, because then one of our terms just goes to 0. I'm thinking of something else in particular here. that kinetic energy equation is 1/2 mv squared. Specifically, it doesn't have a direction associated with it. So if I was in a scenario where I was initially moving, say, in this direction right here, but I end up moving in this direction right here, I could have the same speed in both cases. But my work is doing this weird kind of parabola thing where it's essentially taking away our starting energy and then giving it back again sometime later. So I want to bring this up because you have to look at your picture. You have to be sure of what you're talking about. Some stuff can get a little bit weird here. It's not that any of this is necessarily wrong, right? Some of our descriptions for these things, generally we're talking about work as positive or negative here, but there can be some weird scenarios. I still will heavily encourage you, please, please, please draw out the pictures, describe what's happening in the problem before you actually start writing down a ton of equations. It is well worth it to understand exactly what's happening before you try to solve out anything. So my Control Z is not working, so we're just going to have to roll with those two arrows on the screen now, but that's all right. If we were to solve out for the rest of this thing, we could say, okay, move over that 1/2, move over that m to the other side, and then what we get at the end of the day is the exact same result. And that's lovely, right? Because if I go through two different processes that are both supposed to be correct, and I know you can't see that thing, but you just have to take me face value, there it is. But now I'm kind of like peeking up from the bottom here. It's the exact same result, right? You've already seen this thing. That exact same result is fantastic because otherwise physics is broken, the universe is all sorts of wrong and weird, but that's not the case, right? Doesn't matter which method we use, both of them give us the same answer either way, which is always good. Now, you could argue that one of these methods is easier than the other because one of them is only energy, whereas one of them I have to kind of pick apart which of these equations do I actually want to use. Sometimes that's true, but, you know, there's a few different ways that we could foresee using some of these details. So what that's trying to say, and it's covered up by a handful of things because there's some, well, discard that annotation. There we go. You can see the rest of that now. The math doesn't care which method you use, right? The physics is happy to just work on its own. However, what did we kind of, we put energy on a pedestal to say, hey, this might have some really interesting uses that kinematics can't solve as well. And what was that? Does anybody remember? Or have these been some of the longest 2 days of your life so far? If they have been some of the longest 2 days of your life so far, what we were talking about last time was the fact that what happens when I have non-constant forces or anything like that? That's when energy becomes suddenly very, very useful, right? What if it's not just a linear slope down? What if it has a curve to it or anything else like that? Energy settles all of those things for us. It's wonderful. It's really incredible like that. So, why does energy work so well in some of these things? Well, largely because there are certain cases of what we call conservative forces. And conservative forces are phenomenal, and the biggest one that we're going to be used to talking about here is gravity. That says down there. Let me get to that point a little bit later, actually. Don't worry about it quite yet. Here's the idea. A conservative force is any such force that the energy associated with it or the work done by that force is completely independent of the path taken. So we use gravity as a fantastic example here. Let's imagine these three different paths. Let's imagine I go up, then I go over, right? So, and let me even go to the slideshow on this one, right? I've got these things set up for a reason here. Any path that we could have. So gravity is perfect. Let's imagine we're trying to go back and forth between these two places. We have in our bottom left corner up to our top right corner. Path 1 goes up and then over. Where is gravity doing work? At what section of our path? Not all of them. Only in the y direction. And why is it only in the y direction? Think about that dot product. Think about that dot product, right? When we are talking about going directly upwards, it's backwards. right? But that still counts as work. That's just a negative work being done. So as the object moves up, gravity tries to pull down. That's a negative work being done. As it moves over, the two are perpendicular. The dot product would say that along our x portion of the path right here, can I get this? Okay, just didn't write the first time. Along this x portion of the path, no work is done. Work is equal to 0. But along this path right here, this is saying that work would be equal to the force of gravity times our change of y. Or specifically negative, because it points downwards. Right? So that's all fantastic and great. But, you know, that's exactly what I'm saying right here. What about path 2? What's different? Well, we go over first, but no work is done there either. And then we go up, that's where we see the exact same negative mg delta y. No difference. Right? When the force is perpendicular to the direction of motion, we don't have any work being done. So both of those, the top and the bottom, are 0, whereas the sides are where all the work's getting done. Now, what if we get really crazy? We say, none of this along the axis nonsense. I'm going to go straight there through path 3. Now, this is a little bit more complicated, right? Because, of course, now we're not able to split up into these individual paths. But not to worry, it's a single path the entire time. We would just have to take that dot product. So I would take mg, dot it with r. What I would find here, I need to take that angle between the two, whatever that angle may be, mg r cosine of theta, but then you might notice I have created some triangles here. And if I mess around with these things the right way, where's my angle phi? There's phi. If I take that angle phi, and keep in mind here, what we're saying is the cosine of theta is equal to negative cosine of phi, which is a totally workable thing. That is a trig identity here, because they sum up to be 180 degrees together. What I get at the end of the day is that r times cosine of phi is just delta y again. So this is the big thing about gravity. This is why this is considered a conservative force, because it doesn't matter whether I have gone up and then over, or slanted, or over and then up, or I could go crazy and I could go like this. What if I go underground and then loop back the other way? What if I do like a Hail Mary scenario, right? Any sort of drawing I could put on here. If I start from my initial, I end up at my final. The work done by gravity is always the same, regardless of what path I take. And that's amazing. And we want to talk about why that's amazing, because remember what happens whenever we're talking about the work done is this type of integral right here, right? And this thing can get nasty. Imagine doing the path integral of this semicircular piece that I've just drawn. Yikes. The entire time, every single step along the way, the angle between the path and the force is completely different. So I would have to figure out some way to talk about that path and then the dot product between the two, and then some of it's positive and some of it's negative, and I have to twist my arms a whole bunch of ways to really emphasize how crazy this thing would be. But if I know that it's a conservative force, then I say, hey, I don't care what path it took to get there. All I need to know is the difference between these two states. And I call it a day. So, what that's trying to say there, and now I can kind of pull this thing up, discard all those notations and everything. Now let's read what that says. The work done by gravity does not depend on path, just the change in y. Gravity is a conservative force. So, what if this same path had been friction? What if this was laying on the table, and what we're watching is 3 different paths over a table that's got sandpaper on it or something? What then? What would that look like? How does that change? Does sandpaper mess up anything? Think about from your personal experience here, not just from the picture here. Think about from your personal experience. If I know something's going to be a little bit rough to move, do I want to just move it in one direction and then the other, or do I want to try and go straight there? The longer the path, the more friction will be there. Exactly. Friction does not count as a conservative force. And we can think about this, right? Anytime we're talking about like what it slows things down, it dissipates it into heat and everything else, generally speaking, anytime we're seeing things being dissipated into heat and sound and breaking bonds of atoms and everything else like that, there's a very, very, very solid chance, I would say, I don't want to say 100% because I'm sure there's something that I'm wrong about here, but I would say 99% of the time it's going to be a non-conservative force. Gravity is our #1 conservative force. It's great. It's always there. It's always this constant kind of quantity because the force from gravity is always mg pointing downwards. How do we feel on all of this stuff so far? Are there any questions or anything else like that? I take it we're all feeling fantastic then. All right. So, how do we actually quantify that gravitational energy? It's nothing too crazy. What we're going to say is that it's, at any point, it's mgy. What other forces are conservative? There's a few. Spring force is actually another example, and that's why we're going to get to the spring force next time, just because spring forces are a little bit strange, right? Because it's not constant, but it is path independent. So, anytime we're talking about gravitational potential energy, though, this is a wonderful, super easy thing to deal with. The gravitational potential energy at any point is just mgy. So if I want to know the gravitational potential energy here versus here versus here, all I would have to do is find the height, multiply by mg. That's how much potential energy I've got. So what does potential energy mean? Can somebody give me a description? What do they think of when they're thinking about potential energy? Where does it come from? A stored energy is a lot of ways that it's talked about, but what does it mean to store the energy? Where is it? Is like a gravity a battery when I put it up like that? It's work waiting to be done by gravity. That's exactly it. It's work that is waiting to be done by gravity. When I lift this thing up in the first place, gravity did a bunch of negative work on this pen. My hands did a bunch of positive work. Gravity did a bunch of negative work. That's why right here in the air, it's not moving. The work I did, the work gravity did, they canceled each other out. But now if I were to let go, gravity releases all of that work. Gravity's just waiting to do all of that work back on this pen, and so as soon as I let it release, it flies down. So, that's what we think of in this, right? When I'm talking about gravitational energy and chemical bonds or anything else, very different things. That's for later. That's for much later, in fact. When we're talking about gravity, it is work waiting to be done by gravity. If gravity is given the chance, it will do plenty of work on that object as it falls, but it's waiting for that opportunity. So, concept check here. In order, smallest to largest, the gravitational potential energy of each of these 4 balls. Green arrows indicate a velocity. And that is pretty cool. I agree. I love this part of physics because now we've got a little bit of language to work with, right? Now you guys understand some of the kinematics and the dynamic stuff already that I can really dive into a lot of these details, and we can see some cool relationships in the world. All right, I see some answers so far. 2 answers. Are they disagreeing? Perhaps. Yeah, I like those last answers here just a little bit more. I think those are fantastic. If potential energy, let's write this equation out. If potential energy is just U of G, and that's, whenever we're talking about a potential energy, we oftentimes think about this, we use the value capital U, is equal to mgy. Is there any mention of velocity in that equation? And this is 10-1. No, there's no sense of velocity here. So 3 clearly is the highest. 2 and 4 are both at the exact same level. They share the same potential energy. 1 is on the ground. 1 has the lowest potential energy of all 4 of them. 2 and 4 should be equal potential energy because the kinetic energy has no real bearing on our potential energy. Right? I can convert between the two, But just because I have potential energy doesn't mean anything about my kinetic energy. Does that all make sense? All right. Now, I have been throwing some words around here for a little while now before we've actually defined them. But generally speaking, anytime we have a conservative force, we talk about some sort of, so the full ranking here is 3, 2, 4, 1, or 4, 2. These two are on equal footing. So I have been using this phrase potential energy, even though this said gravitational energy. And the reason I've been saying that is because technically its full name, right? If somebody's mad at it, it would yell out gravitational potential energy. Generally speaking, potential energy is any time I have a conservative force and there might be some work associated with that. So when we're talking about springs are conservative, there is a spring potential energy just in the exact same way. There is an electric potential energy in exactly the same way because that's another conservative force. Any of these forces that are path independent can have a potential energy associated with them. And so it's a really long name to say gravitational potential energy. But if you just say gravitational energy, I'll understand what you mean. That's all fine by me. Hopefully you understand that as well. But it's the same concept every single time. It is work waiting to be done by that force. I have put an object in such a place that if it were to be released, a force would act on it and do work on that object and change its kinetic energy. Gravity are a fantastic example of this, but springs work in exactly the same way, right? If I were to compress a spring and then stretch it out and compress it and stretch it out and compress it, and I bring it back to its initial spot, there's no change. It didn't matter what happened between all of that path or anything else. The spring still is compressed to the exact same amount that it was at the beginning. So, anytime we talk about some sort of change of potential energy, it is essentially the negative of the work done by the conservative force the first time, which is a little bit complicated, but think again about this description, where I said, when I lift up the pen is here, I start to lift up the pen. I did some work on it to raise it up. Gravity still pulled down the entire time. Gravity did a bunch of negative work on this thing, stored up, waiting to be used. Once I open that, then gravity's allowed to do that work again, and it all spills back out. What about a spring inside of an engine and the intake and the outtake valve? I am not entirely sure of all of the mechanics of that piece, but I'm not entirely sure on that one. If you can find a good picture, or we can talk about that one after lecture, I can talk about that a little bit more specifically then. But generally speaking, anytime a spring is at the same spot as it was before, that's the same amount of energy. Listen, nobody's on Shaggy level. Come on. But let's get back onto the point here. Since we have any of these things, really what it comes down to is that the energy of a system is always conserved. If there is work to be done by some external force, there might be some sort of potential energy associated with that, depending on how we're talking about it. You know, sometimes it really just depends. If we're thinking about something like gravity, we always live to think about the gravitational potential energy. If I'm just, I don't know, like pushing on this thing and then changing or anything else like that, that's not necessarily conservative. If I have an applied force or something else like that, sometimes we talk about those things a little bit differently. So I just want to kind of bring that up. The name of the game here, though, is energy conservation. Any energy that I put into this thing is transformed between all the different states, right? And this is my big point right here. This is really what I'm trying to get to. What we have been talking about is what's called mechanical energy, as compared to something like thermal energy, right? Thermal energy is a little bit different because that's associated with heat and temperature. That's not what we're talking about here. We are talking purely about kinetic energies and potential energies. And I say kinetic energies because that's a little bit of foreshadowing. We'll get to that soon. Generally speaking, anytime I have an object, if there are no external forces, if there is no extra work being done on this thing, then the mechanical energy will be conserved. I can transform between these forms of energy. That's totally fine, right? Compare the difference again. This object is sitting up here with a bunch of gravitational potential energy. As it falls, There goes the pen completely. That's rolled down pretty far into the floor at this point. All of that potential energy was converted into kinetic. But the amount of energy that was in there stayed the same the entire time. And that's the important point, right? We can use that to tie together different states in our problems. So, two ways to write that out. You could either say the change of energy is equal to 0, or the total kinetic and potential energy at the beginning is same to the final kinetic and potential energy. What I was saying with that one is that the energy, the total sum of the energy is always conserved. If there are no external forces acting on it, and when I talk about external forces, I'm talking about some sort of extra work being done, a non-conservative work being done. But we'll get to that in a minute. As long as we're talking about conservative forces like gravity and kinetic energy, the amount of energy an object has will be constant. Two ways to write it out are either change of mechanical energy is 0, or the total energy at the beginning is equal to the total energy at the end. How do we feel on these points so far? Where did my pen actually go? Oh, geez. Oh, that's way under. That's going to be our joke for the rest of the semester, isn't it? All right. So, I want to try this thing out in a problem here. You know what? If it increases engagement of the people responding in chat and everything else, I will absolutely take that one. Let's imagine a fully grown adult, right? Not just a child. A fully grown adult reaches out of a window and tosses balls straight up, right? Because we have decided, why do children get to destroy things? And why do we get to forgive them? Why can't we destroy things? We're going to destroy our own things. We're going to toss something up into the air with a speed of 10 meters per second. The window is 20 meters above the ground. So, right, we're not doing this on like ground floor or anything else. We really want to break things. Use energy to find the ball's maximum height above the ground. The ball's speed as it passes the window on the way down, and the speed of the ball when it impacts the ground. Can I demonstrate? No. No, I don't think so. I don't have anything good to throw. Not on my desk right now. Not things that I am not worried about, like breaking in some way or another. Unfortunately. That's getting a little bit more illegal here. So, what I want you to do, think about this thing. Use our conservation of energy thing right here, right? All of this good stuff. Know that the energy of the ball stays the same the entire time. The total mechanical energy never changes. So between the kinetic energy and our good friend gravitational potential energy, think about how much energy we start with. Use that to find these other 3 points. I'm going to say the next 4 or 5 minutes to work on this one, and then we will come back together and see what you got. All right. I think it is a fantastic time to dive into this. So, we need to talk about how all of our energy starts, how all of that stuff, come on, see the window, see the window. Please? Is it going to freak out like this? Is it really going to? I know it sees the window. Hang on. Capture method. It's not that one instead, is it? Does that still work? Okay. No, it's just my computer trying to stop me. It's the constant struggle. Every single day I try to do anything, this computer says no. Sometimes it's just like, we'll just disconnect the USB devices. It's fine. He didn't need them. So let's take a look at what we've got here. Let's draw ourselves a good picture. How else are we going to do this? But let's draw kind of like this. So I have to imagine, because we are tossing things out of a window with the intention that it's going to fall towards the ground, I have to imagine we're taking the utmost safety precautions for doing this, and we are probably leaning like back facing out of a window, kind of like this, throwing the ball upwards like that, right? That's not the ball, that's the person. The ball is, let's do this in, let's do a bright orange color right here. So it starts with some initial velocity pointing upwards, right? And it's got some initial height. Call it y naught. So our whole point here, right, there's a few different scenarios we're looking at here. We're looking at first, where is it at a maximum height? At our maximum height, what do we know about the maximum height? We have done this in kinematics before. What's our big sticking condition that we know we're at the biggest, the tallest point? When the velocity is equal to 0. Exactly. And let me talk about that one a little bit more in just a little bit here. We've got a brand new way that we can describe that one that will maybe tie in together a little bit better with some of our old kinematics. Then at a certain point, we pass by the window again, so we know our velocity is probably going to look something like this, and then things speed up as they fall, right? Have you guys had the same experience in reality? I would assume so, because, again, as far as I know, there's only one reality. So we can imagine this is kind of the progression as time goes on of what we're expecting to see here. I know we talked about throwing this thing straight up, and I have done a little bit different than that, but let's imagine this is like our time axis, for example. If we need to get really crazy and imagine that it's actually on a graph. But anyways, right before it touches the ground, I can imagine that the velocity is probably a little bit bigger than normal. So, our whole point here, energy conservation. In black, please. Name of the game. Energy conservation says anything we start with, we are going to hold on to for the entire time. So let's think about what do we actually start with here. And let's go ahead and write out some of our given variables while we're at it. We know that our initial height is 20 meters. We know that our initial speed is 10. That is to say, any energy that we start with, energy initial, is equal to energy final, whatever final state we want to call it. So, for example, let me look at my very top point right here. My very top point right here, that's basically saying, okay, any energy that I started with, mgy, whoops, not A, mgy, potential energy plus the kinetic energy that we started with, 1/2 mv0 squared. That's our starting energy. At the very top, we know that all goes back into potential energy. Our velocity is 0. So if we call this that, then we say m, g, y final. The m's cancel out. What I can find, for part A at least here, that my y final, my tallest point, would be equal to gy naught plus, whoops, not gy naught, the g gets canceled out, just the y naught portion, plus 1/2 v naught squared divided by g. I divide all pieces by mg. This is what I'm left with. That's my expression for the final height at the very, very top. Does that all make sense so far? Does the reasoning make sense at least? The value that we should get when we plug all of this good stuff in is 25.1 meters. On the way back down, how fast are we going? Not even going to write out an equation. How fast are we going on the way back down? G did cancel with the y naught portion. It doesn't cancel over here, right? That's another term. The speed falling down is 10 meters per second. Think about it like this. Part B here, if we wanted to write it out like this, I could say mg y naught plus 1/2 m v naught squared is equal to, we're back at our original height, so mg y naught plus 1/2 m, do this in red to say, hey, this is a mystery, who knows what this v is? What does it have to be? What does it absolutely have to be to make sure that equation is equal? Our velocity on the way back down must equal our original velocity. Or rather, our original speed is what I should be saying. Velocity has changed direction, but our speed has stayed the same. Where did the 1/2 v squared come from? Remember, that is our expression for kinetic energy. That's just our expression. For any time we've got kinetic energy, that's the expression that it takes. 1/2 mv squared. So for part B, our velocity here must equal, or rather, I keep saying our velocity when I should be saying our speed. Our speed should just be 10 meters per second. That's it. Kinematically, we could do the same thing. We could say the delta y is equal to 0, and then v, the initial times t plus 1/2 a t squared, plug in all of that stuff, and we could find the exact same answer. But realistically, energy works even better for this. Right? And another way that we can think about even part A here is all of our descriptions when we talk about, we know we're at the highest point because we're all the way up here and our velocity is supposed to be 0. But now the other way to think about this is that all of our energy has gone into potential energy. There's no more kinetic energy. It's not going to go any higher than this. To go any higher than that means we had to have added more energy, and that doesn't happen. Energy is conserved. But yes, so that expression that we've got here, that is our potential energy and our kinetic energy when we start initially at the window. Part C, last one here, it's kind of like A actually. It's probably more similar to A because now what we can say is that, all right, well now we're at the ground, right? We're at y is equal to 0. So our initial energy, as we started at the window, way back when, 1/2 mv0 squared. Now, all of this has gone into kinetic energy. There is no potential energy left. 1/2 mv final squared. Our final speed then, same way as before. We can say that this expression, final speed, this one is a little bit nastier, I would say, is equal to square root of 2g y0 plus v0 squared. When you go through all the algebra for this one. But this expression just shows up in the exact same way in some of our other writing from before. What we find for our final speed for this one, 22.2 meters per second. So, why did we bother to learn kinematics in the first place? Right, what was the point? When energy was here doing all of this stuff, why would we even think to work with kinematics? Not just suffering. Right, realistically, it's another tool. Kinematics, describing how something moves, is very easy to do because we can visually see it. We can make these things happen. We can recreate all of these experiences. To talk about something like energy is a little bit more of an abstract concept. How do you measure energy in the same way? Right, I can measure speed. I can say, well, it was here, then it was here. I take the time difference between the two. That's the speed. If I'm thinking about something instead like energy, I have just given you that it's 1/2 mv squared, and we kind of take that at face value at a certain point, right? I have no way to necessarily measure that energy, not in the same way. I don't have a good way of measuring potential energy, not in the same way. A lot of these other details are a little bit more abstract. And tying all of these things together, these are all, for one, it was a little bit easier and a little bit more, concrete to start with kinematics, but also it's another tool. There are going to be times where dealing with those forces and the different works, and if they're changing direction and all that stuff, that's insanity to deal with. But perhaps a time change in acceleration is a much easier way to approach a lot of these problems. It is a different type of tool that you might need to use for some of these pieces. Because a lot of what this has done, this hasn't really told us anything about position or anything else like that. Kind of, but it's a little bit rough. It's not quite as fine-tuned in the same way, right? That v squared kind of brushes over some of the details, like the fact that the speed can change direction and we can't tell. So they're different tools for different situations. Oftentimes, we are going to find energy is a fantastic tool. It works very quickly. It does a very good job. But we already have to have a good grasp on our kinematics, what we expect to happen in the motion of the object, before we can properly use energy. Because if we didn't know any better, we could say that when we come back down, our velocity is pointing the opposite direction, and the equation wouldn't disagree. The equation would be like, yeah, that's fine. You know, you threw it up and then it started coming back down, but suddenly it reversed. Yeah, that's fine. No big deal. It doesn't work like that. But we know it doesn't work like that because we've already had our experience in kinematics. But now, hopefully, with all of these details, we can start to, it's a big web. We're weaving all of this information together. So if perhaps it was a little bit more difficult the first time through, if you go back to a lot of that kinematic stuff now, I can imagine you can weave in some of these energy details, and a lot of those older concepts will make a lot more sense now. But we have to start somewhere. That's the reality of the situation. Are there any other questions on this thing right now, though? How's the vibe? All right. So, yeah, no vibe, no violent vibe check this time. I think it sounds all right. So, with all of this stuff in mind, let's imagine I throw a ball 3 different ways off of a cliff. Different speed, or different angles, same speed. What is the speed of each of these from smallest to largest just before they hit the ground? So, here's what I'm thinking. In all 3 cases, I start with a potential energy mgy. In all 3 cases, I start with a kinetic energy 1/2 mv squared. In all 3 cases, I end up at y is equal to 0 and some final velocity, final speed as we hit the ground. Now, the angle of these things does not have to be the same. But at the end of the day, the energy we started with, the energy we ended with, is all the same. All of them should have the same speed as they hit the ground. Energy conservation at work. Does that all make sense? I'm not entirely sure if that was a typo or something. It's energy conservation in this case. All 3 of them started with the same amount of energy. All 3 of them end with the same amount of energy. They all end at the same spot, right? They all end at y is equal to 0. But because at the end of it, I shouldn't even say it's the, I drew this wrong. It should be y is equal to 0, not y of 0. Y is equal to 0 in this case. All of their energy is kinetic energy by the very end of this. So it's a 1/2 mvf squared is equal to the same starting energy. If it's all in kinetic energy, then regardless of what angle it was thrown at, it ends at the exact same speed. But we can kind of see from the trajectories that the angles will be different. And that's totally fine. If I said right before it hits the ground, so when we're saying right before it hits the ground, we're talking before the collision has happened, but like when it's within, I don't know, an atom spacing between it. So let's look at one more here. Let's imagine you're driving in particularly icy conditions. And I need to make sure that you guys can see exactly what we're doing here. You're on the run, right? You can't afford to get caught. Not with this child. So you're going at 35 kilometers per hour because we like metric units a lot better than this. When the road suddenly descends 15 meters on a slope into a valley. So that is 15 meters directly down at some sort of slope. You take your foot off the accelerator and coast down the hill. Just as you reach the bottom, you see a policeman hiding behind a speed limit sign that reads 70 kilometers per hour. And for some reason, you were driving half that before you hit this hill. What is your speed when you pass the cop? I'm going to give you guys just say 3 or 4 minutes to work on this one. Conservation of energy, again, very important here. Use that to find your speed as you pass the cop at the bottom of the hill. Go ahead and get started. All right, team. So let's talk about this one. We've got 15 meters, but 35 kilometers per hour. Not a standard units, and since I am doing something more transformative, right, rather than just setting two speeds equal to each other, I need to actually do this conversion. So let's go ahead and draw this thing out. The whole idea here is that we're not necessarily on, like most hills, at least the ones that I have driven on, don't just go from a straight flat road to suddenly angled downwards, right? You would probably destroy your car that way. Instead, I would imagine a lot of these things are a little bit more shaped kind of like this, something or another. That's probably still a little bit too steep for what I'm intending here, but the general idea is that it doesn't just immediately drop straight down into an incline. It kind of slopes into it a little bit. So we start up here at the very top. We know that the height difference between here and the bottom of the hill is 15 meters. Let's just call it h for now. We know that when we start, we have some initial velocity, call it v0. We know at the very bottom of the hill, we are similarly going to have some sort of final speed, or final velocity, if you will, vf. That's what we're looking for. 35 kilometers per hour. Dumb unit. Doesn't work very well for what we're liking to use it for. So we're going to convert that into meters per second, and if we do that, we should find that this is equivalent to 9.72 meters per second. Our initial height, 15 meters. So I use my best friend, energy conservation. I'm looking for VF. I know at the bottom of the hill, I will have essentially expended all of my gravitational potential energy. At the very top of the hill, I start with gravitational potential, mgh. I start with some kinetic, 1/2 mv0 squared. I end at the bottom of the hill with no potential, all kinetic, 1/2 mv final squared. We don't need the mass, can cancel that out. I'm looking for v final squared, so I multiply everything by 2. I divide everything, or I take a square root of everything after that. That is, V final is equal to square root of 2GH plus V naught squared, square root of that entire thing. When we do that, we get 19.71 meters per second, converted back 71 kilometers per hour. Mamma mia. We're running from the cops. Reading problems aren't linked in the calendar. There are no reading problems with this one today because I boofed the order. So what it turned out to be is that we changed the order from the book in this one. The book, at the end of chapter 9, it kind of assumes some things from the beginning of chapter 10, but it wants to keep things cohesive, and we're not a big fan of that because it's a little bit more confusing than we think it needs to be. So it should have been 9-1 stuff, then 10-1 stuff, then 9-2 stuff. But since I put that wrong in the reading for the calendar, I have just scrapped the reading from today. The next reading for Monday will have a little bit of stuff from both of them. So the last thing that I've got on this one is that we do have, it is not actually called Fat Skateboarding. It's a little bit more fun than that. You are welcome to work with a group with this thing. You're welcome to work by yourself. Again, this is kind of true for all of the labs. If you're doing these things for homework even, I encourage you to work with friends if you are interested in doing any of that stuff. I shouldn't have left it as a group. You are welcome to work with it as a group if you would like, but because we are not set in groups anymore, it doesn't quite work quite in the same way. But it's a fun little thing on that one. It's another PHET simulation. You get to see some of this difference between potential and kinetic energy as somebody skates around, does all of that good stuff. You know, mess around with it a little bit, have some fun with it, see some of the things that go into it. But otherwise, other than that, that's what we got for the day. You're all free. Figure we would get finished a little bit early for a Friday here. So in a little bit of time to work on this thing, it shouldn't take you too long at all, but a little bit of fun to mess around with the simulation. But yeah, have a fantastic weekend, everyone. I will see everyone again on Monday.